Continuing our discussion of renewable energy sources, in this lecture we'll talk about tidal energy and other sources of ocean energy, such as wave energy and thermal energy. Ocean energy is a form of renewable energy that isn't much used in the United States, but the technology exists and it is used to a limited extent in other parts of the world. We'll describe how tidal barrages work and tidal turbines work, where they can be located, and how their environmental impacts differ. Oceans are abundant sources of renewable energy, and oceans have the potential to generate energy reliably. All forms of ocean energy have the advantages of being non-polluting and not contributing to greenhouse gas emissions, aside from the processes used to construct them in the first place. To take advantage of ocean power, you need coastline, but 44% of the world's population lives within 150 kilometers of the coast, as shown in this map. So that's not a major barrier at the global level. However, ocean energy is currently more expensive than other forms of energy, and no data on the energy return on investment for ocean energy is publicly available. There are three main ways of getting energy from the ocean: tides, waves, and thermal energy. Of these, tidal energy has been the most widely developed. Both tidal barrages, which are an older technology, and tidal turbines, a new technology, are used, and we'll talk about each of these over the next few slides. Ocean thermal energy conversion uses the temperature gradient between cooler deep and warmer shallow waters to run a heat engine and produce electricity. Currently, there are only two fully operational thermal energy conversion plants operating, one in Okinawa and one in Hawaii. The top photo shows the plant in Hawaii, which powers 120 homes. Several larger projects are planned with this technology. Finally, wave energy is attractive, but not yet commercialized. It is extremely difficult to engineer storm-hardy installations for a rough saltwater environment. However, this energy source is likely to be developed in the future. The bottom image shows a wave energy converter at a U.S. Navy test site. Tides are the rise and fall of water resulting from gravitational interactions between the sun, moon, and the earth. How big the height difference is between high and low tides depends on the face of the moon, the season, and the local underwater topography. We call this height difference the tidal range, and this map illustrates the global tidal ranges. The first way tidal energy was exploited was via tidal barrages. Tidal barrages are limited to places with large tidal ranges greater than 3 meters. Those are places that are dark orange or red on the map. Notice that the U.S. doesn't have many places with this large of a tidal range, so we have no tidal barrages in the U.S. On the other hand, you can see that parts of the European, Canadian, and East Asian coastlines have the required large tidal range, and that's where we find tidal barrages. South Korea has the largest tidal barrage, producing 254 megawatts. France has the oldest tidal barrage, producing 240 megawatts. Canada has one tidal barrage, producing 20 megawatts. And China and Russia also have smaller tidal barrages. So how do tidal barrages work? They are like a dam that blocks an inlet or lagoon. Energy is generated by both rising and falling tides. When the tide is rising, water moves past the turbines and into the bay. Then, when the tide goes out, water moves the opposite direction past the turbines. Both directions, the turbines can transfer their energy to a generator and produce electricity. The regularity of energy generation is a big advantage of tidal barrages, but they have serious environmental drawbacks. They change water levels, muddiness, and plant and animal movement in the bays that they block. The presence of the barrage also affects navigation and recreation. These drawbacks, combined with a limited number of places in the world where the tidal range is sufficiently large, means that tidal barrages are unlikely to become significant renewable energy sources at the global scale. However, in places where storm surge barriers have been built, or are being built, there is a potential for adding turbines to generate electricity. This is much the same principle as building a flood control dam and also using it to generate hydroelectricity. An example where this has happened is at the Oosterschelde barrier in the Netherlands, shown here at the bottom. Tidal turbines show great promise for deployment in more locations than tidal barrages. Tidal turbines work on similar principles to wind turbines, except they are more expensive to build and deploy because water is denser than air, so the turbines have to be much stronger and heavier. Turbines are placed on the seafloor where there is strong tidal flow. This is often in narrow openings to concentrate the tidal power. The image on the right shows a turbine being deployed for testing in New York's East River. In 2015, the company installed 30 turbines in the East River, which connects Long Island Sound with the Atlantic Ocean, and where strong tidal flow exists. The project provides 1 megawatt of electricity, powering 9,500 New York homes. There have been concerns about impacts of spinning blades on marine life, but so far studies have found minimal impacts to fish and marine life because they tend to avoid these areas during times when the strong currents are turning the blades, and because most of the turbine designs have very slowly moving blades. But large-scale installations may be more problematic. The first commercial tidal turbine was installed in 2008 in Northern Ireland in a narrow strait with swift currents, as shown in the top left image. The turbine blades could be rotated by up to 180 degrees to match the directions of both the rising and falling tides, as illustrated in the bottom left image. This allowed the turbine to generate 1.2 megawatts of electricity for 18 to 20 hours per day. It ran from 2008 to 2019 when it was decommissioned. The Northern Ireland project was critical in informing the design and installation of the world's current largest tidal energy array, which is between Scotland and the Orkney Islands, in an area where tidal currents can reach speeds of 5 meters per second, or 11 miles per hour. One of the turbines is shown in the top right. That project already powers 3,800 homes, and an expansion is planned. Other turbine designs are currently being tested. The bottom right image shows one such design that was tested off of Nova Scotia. To summarize what we've learned, the ocean is a major potential renewable and reliable source of energy, with energy harvesting technologies that don't create air pollution or greenhouse gases after installation. However, ocean energy generation is technically challenging and expensive, and no energy return on investment data are available. Of wave, thermal, and tidal energy, tidal is the only one being used commercially at this point. Tidal barrages have limited applicability and big environmental impacts, but tidal turbines are of increasing interest for commercial development. Their challenges remain to scale up and make them economically competitive with other forms of energy.